pleasure to introduce Romyar Sharifi from Arizona. He's shortened his title. He's going to talk about the first part of what's announced. He's going to talk on reciprocity maps.
Thanks very much.
Okay. Right. Thanks very much for the invitation. So, what I'd like to talk about are, well, not classical reciprocity maps, but reciprocity maps for extensions of number fields unramified outside a set of primes, or at least what I call reciprocity maps. So, I guess the point of this talk will just be to give some advertisement for them. Let me start by describing the analogy with local class field theory. So suppose, for instance, that f is a finite extension of QL for some L. And let's let GF be the absolute Galois group. Of F. So as you all know, I mean, we have a reciprocity map in local class field theory. Rho F, which maps, we can take it to be the completion of the multiplicative group, the profinite completion, to GF ab. Okay, it's the abelianization. So now how can we, let me just give you one way of defining this, which may be familiar with. So suppose I consider the map, suppose I consider the map pi from the absolute Galois group to the abelianization, which is just restriction. Okay, and then I consider the continuous cohomology. And let's to do everything at once, let me take this with z hat 1 coefficients. And then what I'm going to do is I'm going to take a cup product with pi on the left. So that'll take me to H2, continuous cohomology of GF, with coefficients in z hat tensor this, which is just going to be GF ab twisted by 1. Now, of course, GF acts by conjugation on GF ab, so I mean it acts trivially. So, and since the cohomological dimension of GF is 2, this is the same as just continuous cohomology coefficients in z hat 1 tensored over z hat with GF ab. So, so what we have here is, well, this group, okay, this group is f hat cross. And this group, well, I mean, because, well, H2 gives you the Brouwer group, this group is z hat. So this group is GF ab. And this map is the reciprocity map. Okay? So that's one way to define the reciprocity map in local class field theory, at least when you're avoiding the characteristic, and I've done that by taking characteristic 0. So, so what I want to talk about here is the idea of an S reciprocity map. So now I'm going to fix a prime P. I'm not going to do everything at once, because I can't. So let's let P be a prime, and let's let F be a number field, which will assume just primarily to make things simpler, avoid writing some things, to be totally imaginary if P is 2. OK. And let's let S be any set of primes that contains the primes above P. So S, a set of primes of F containing those dividing P. Okay, and then the absolute Galois group is going to be replaced by the Galois group of the maximal unramified outside S extensions. So this is the Galois group of the maximal unramified side S extension of F. Okay, so need one more object, or two, I guess. So the maximal abelian pro-P quotient of this will be denoted by X script XF. So this is the maximal abelian pro-P quotient of GFS, or in other words, the Galois group of the maximal abelian pro-P unramified outside P extension of F. And finally, UF will be just the group of S units. So the P completion. So P completion of the S units, so units outside S in F. Yeah.
S contains, you have this distinction with what happens at the infinite prime, so.
Right, well, I've avoided all, right, all primes are complex. All infinite primes are complex because I mean, that will matter in my cohomology because I'm going to be taking P parts. So.
Just, well, complex if P equals 2, but it does not. You always, so your set of primes is really, this GFS is pi 1 of spec OK minus S. Is that correct?
Yes.
Okay.
Or OF. Yeah. That's right. Okay. So I can now define the reciprocity map. Okay. So right. So the S reciprocity map for F and P is a map, call it psi sub F, and it'll map the S units to the continuous cohomology of GFS with coefficients in ZP1 tensored by XF. Okay, and how do we define it? Right? So, well, we define it by taking that chi to be the natural surjection, right? And let's consider the cup product. Left cup product with chi. So let me write out explicitly what we have. So we have H1 continuous cohomology of GFS with ZP1 coefficients. We're going to take left cup product with chi. So where is that going to land me? That's going to land me in H2 continuous cohomology GFS XF twisted by 1, which again, XF is acted on trivially by GFS and cohomological dimensions 2 because of my assumption, so I can pull out the XF, right? So this is H2 continuous GFS ZP1 tensored by XF. Okay, so I'm doing completely the same thing. I mean, now the point is that this H1 is UF, and this H2 is, well, it's just H2. And I'll describe that in a second, but there we have the map, right?
In the case you are in, is group cohomology the same thing as étale cohomology?
Yes. Right, yeah, this is, we could just as well use étale cohomology.
You're taking S to be finite or not?
Oh, yeah, sorry. That should be fine. Okay, so let me just say what H2 is. So if I let YF be the, well, easiest way to define it at this point would be the maximal quotient of XF in which all primes in S split completely. So for the maximal, so in other words, what this is YF is the Galois group of the maximal unramified abelian pro-P extension of F in which all primes above S split completely. So in other words, YF is isomorphic to the P part, the finite group. It's isomorphic to the P part of the S class group of F by class field theory. And so by S class group, I mean I take the class group and I mod out by the classes of the primes that lie in F. Okay, so now there's an exact sequence. YF sits inside the continuous cohomology with coefficients in ZP1, maps to the direct sum over V and S of ZPs goes to ZP goes to 0. I mean, what this, another way of saying this is sort of the tape module of the P part of the S Brouwer group. Okay, so this is coming from the, well, this is coming from the long exact sequence. It's in, well, the Poitou-Tate sequence, for instance. Okay, and this is the Brouwer part here. So in particular, if there were only one prime in S, then H2 would just be this P part of this S class group. This is the sum.
So from the étale point of view, that's a cohomology with compact support.
Right, right. The cohomology with compact support shows up here, and this is the co-kernel of the map from cohomology with compact support. Yeah. So, right. Okay, so I mean, well, what do these maps do? So suppose, for instance, I mean, here's an easy thing. Suppose that chi max f is a home. Well, this is a different chi, so I should have given that another name. But anyway, suppose that this is a homomorphism. Okay. Well, let's let chi tilde denote left cup product. So this, I'll use this later too, with chi. Okay. So we have a commutative diagram. So if I apply my reciprocity map, so on the one hand, I can do that. On the other hand, I can take left cup product with chi And since, so this is supposed to be a trivial ZP GFS module. So it has trivial action. Then I can do the same trick with the cohomology and pull the A out after I take cup product. And then I have an obvious map here, which is identity tensor chi, and this commutes. So the point here is somehow that psi f interpolates
Criterion is the cup product with chi composed with the old chi. You have to start.
right. This chi is a different chi, right? So yeah.
But you use both chi's.
Yeah, I'm using that chi, the other chi here. That's my psi f, and this is my new chi.
Yes,
The
but
new
you
chi
can
starts
think
from
that-
XF, not from GFS.
So the chi in the tensor product is the
Right.
down.
Oh, sorry. Okay, so yeah, I should say, right. So HOM from XF to A is equal to HOM of GFS to A, which is H1 GFS A. So chi tilde is left cup. So I'm viewing chi here when I'm defining chi tilde. I'm taking cup product with this element of H1 with coefficients in A. So this group is H2 with coefficients in ZP1, right? And now I'm taking cup product with this element here, H1 GFS A lands me in H2 GFS A twisted by 1, which is this group. Yeah.
UF is equal to H1.
Oh, sorry, H1. Right. Okay. So, okay. So, I mean, in particular, let's see if that's what I want. Right. I mean, so in a particular case, so let's say that E over F is an abelian. Let's say E over F is abelian on ramified outside S, and G is the Galois group, right? And now let's suppose that I'll give it a different name. Lambda, right, is the map which takes XF onto G by restriction. Then I get a map, right, lambda tilde, and, well, I'll define psi E over F to be lambda tilde. Okay? So this is a reciprocity map for the given abelian extension. Okay? Right. So now, of course, in local class field theory, again, you have reciprocity maps for any abelian finite extension. I mean, let's say that E over F is finite. I mean, then what happens in local class field theory is that the map rho E over F will take the norms from E over F to 0, right? Well, in fact, it is true that psi E over F takes the norms of the S units in E to 0. But it's not true that this is the kernel of the map in general. So okay. So one other thing I need, I want to give you a formula for this map in the case that E over F is cyclic. So, but for that, I need to realize that this map is sort of a combination of two maps. One which maps to the Brouwer part, and one which maps here in some sense. So, I mean, and if I take the projection of this map, right, to the Brouwer part, so I map to H2 and then I map to this part here, what I recover is the maps of local class field theory at the primes in S. So, right, so that part is understood. So let's let UE over F be the set of U in UF such that my local reciprocity map, let me just say I've chosen some prime over V, which I call V, I completed that prime, that this local reciprocity map applied to U is 0 for all V in S. Okay? And this implies that they're all 0, in fact, because it's an S unit. So not just in S. But anyway, these things are exactly the elements that map into YF, whose image under psi lands in YF. So psi EF induces a map psi EF, I'll just call it 1, which is just the same map, but now it's a map to YF. And I need to be a bit, no, that's fine. It's this tensor XF. Okay? So I'll give you a formula for this map. So this is just a rephrasing, what I'm going to write, of a result of several years old result, quite a few, maybe more than several, with McCallum. So suppose E over F is finite cyclic and unramified outside S. And a P extension. But I mean, I already said that. OK. So for U in this U E over F, it turns out that because a local norm everywhere in a cyclic extension is a global norm, that we may write U as a norm from the extension. And we may then write this element in E. This is an element of E, not of UE. We may write this element of E, well, it's ideal, it's S ideal, as some ideal with sigma minus 1, or a 1 minus sigma applied. So this is the Galois group, where so A is some ideal, and sigma is in G, the Galois group. OK, so it's in the augmentation ideal applied to the ideal class group. OK, so then the formula, I have to remember, end up with an element of H2 tensor G, or actually YF tensor G. So is just that I take the norm of this ideal down to F. I take its ideal class, and I tensor with sigma. So that's the element of G. So that's the formula. So this is the ideal class, S ideal class. I'm using class field theory to identify this with that Galois group. So it's a simple formula, but somehow it's not very easily computable. It's not very, yeah.
On the left-hand side, the row is the local reciprocity map, or in the definition of U.
Yeah, that's the local reciprocity map.
On the same board, in the target of psi y,
Mm-hmm.
probably YF tensor G.
Right.
Oh, yeah, sorry. That's definitely a G. Thanks. Yeah, I'll also have a psi F1, which maps to the YF tensor XF.
This lambda symbol, this lambda is kind of chi here. Not a chi, it's a chi.
Lambda is a chi. Yeah?
The equality is more or less the identification in tensor chi.
Right. Yeah, just like that. Okay, so let me explain this in terms of the way I originally thought about it for a second, in terms of cup products. So, cup products. And an example. So the point is that psi f interpolates, and we've kind of already seen that, cup products. Well, let's suppose that, for instance, the p to the nth roots of unity were contained in F for some positive n. And, well, in that case, I have a cup product pairing, which just results from a cup product. It takes UF cross UF. So it's a cup product on the H1 group I've been considering with values, but instead of in H2, ZP2, so that I'll have trivial action, I'll reduce it mod p to the n. So the cup product lands in H2 GFS mu p to the n tensor 2. And so that I've reduced mod p to the n. Now I can pull out a mu p to the n. So this is H2 GFS mu p to the n tensor mu p to the n. OK. Well, what is the cup product then? So let's suppose that if I have A in F, well, in UF, okay, if I have A in UF, I'll let the Kummer character attached to A be chi sub A. Okay, so chi sub A is the Kummer character, which acts on p to the nth roots of A. Okay, so this cup product pairing then is just the value of this reciprocity map. So in other words, A, B, p to the n, f, s is chi A tilde, defined as I just erased, chi A tilde of psi f of B. Okay? So in other words, this map, psi f, gives you this entire cup product pairing at once. It tells me what the cup product of any two elements is. I apply it to B, and then I apply this character here. Okay? Right. And the reason I'm saying this is because in simple cases, this is quite interesting. So, I mean, let's take F to be Q mu P for P odd for a second. So McCallum and I made the following conjecture. So let's let S be the set consisting of the prime above P, 1 minus a pth root of unity. And the conjecture is that the span, in this case, the span of the image of this pairing contains the minus part of the class group, the minus part twisted by, the whole thing now, there's no H2 component. We just have 1 prime. Contains the minus part twisted by mu p. OK, so minus, I mean, here there's a unique element of order 2 in the Galois group of F over Q. If you like to think of it as complex conjugation, I can do that and then take the minus part. OK, what do we know about this? And I'll say, hopefully, if I get there, a little bit more about this later. This holds for p less than 1,000. In fact, if I take a particular field, psi f adjoin a pth root of p over f, this is surjective. for p less than 1,000, and this implies conjecture holds for p less than 1,000. In other words, pairing with p is surjective already. Okay. That's not something I'd expect to be true in general. Okay. So since I'm advertising, at this point I'd like to give you a curious and much more recent property that it's not, it was always there, but much more recently discovered property of this map. Okay, so for a particular extension, so I want to take a particular Galois group G, a particular E over F. So let's let E be such that the Galois group of E over F is YF. In other words, it's the Galois group of the maximal and ramified abelian P extension in which all primes over S split completely. It's the Galois group corresponding to this P part of this S class group. In this case, since the elements generate locally split extensions, already the map psi F or psi E over F takes elements of U F to the, well, trivially under the local reciprocity maps. So in other words, they land in YF. So in this case, U E over F equals UF. Okay, so I don't have to restrict anything. Right, so I get a map. So my map psi E over F, 1 if you like, maps UF to YF because it lands in YF, tensor over ZP with YF because that's my Galois group. Okay, so now I have a map to YF tensor YF. So here's the interesting result. Follows from another result, which I won't talk about. But so, well, what can we say about this map? The image of psi EF 1 lies in the anti-symmetric part of YF tensor YF. In other words, it's sums of B plus tensor A's minus A tensor B's. So this is not expected, this is not something simpler like the cup product is anti-symmetric. That doesn't give you this. Let me tell you what this is actually saying in terms of cup products. Right, so suppose again mu Pn is in F, and let's let A, B be elements of F cross, or sorry, UF, with A and B P to the nth powers in E. In other words, they generate, the P to nth roots generate a subfield of E. Okay, then for any U in UF, what this is saying is that if I take the cup product of, let's say, B with U. So now I have to view my chi A and chi B as maps. Okay, so they factor through YF, and they would go to YF tensor mu Pn. But since I want to apply them to somehow YF tensor mu Pn, where the cup product pairing lands, so they'll map YF tensor mu Pn to mu Pn tensor 2. I mean, as groups, this is all the same. Right? So I have this value of the cup product pairing lands in here. I apply chi A to it. then I get minus what I would get if I applied chi of b to the cup product of A with U. Okay, so another way of saying that, well, one interesting point is, say I took f to be q mu p. And just an aside, I mean, say p divided two Bernoulli numbers, okay, which means that there's two non-trivial eigenspaces, not just any two, but two non-trivial eigenspaces, odd eigenspaces of yf under the action of gal f over q. What this will do is it'll relate a cup product with values in one eigenspace to a cup product with values in the other eigenspace. And it'll say 1, 0 if and only if the other is 0. So it's an interesting property, I think. OK.
But what is the actual relation between the two eigenspaces, can you say, in that case?
Well, in general, there's no known relation. It could be any two that are non-trivial. And you don't, I mean, well, I mean, if you want to talk about particular values, I was just saying one value will be non-zero if and only if some other value. If you really want to talk about particular values, then you want these extensions to be generated by roots of cyclotomic p units. You should probably assume Van der Waals conjecture for the two given eigenspaces, and then you can say something specific about two values that you know. Let's see, where was I? Here. OK, so on to other things. I want to talk now about Iwasawa theory.
Will you tell why this is true?
Hmm?
Will you tell the reason why this is true?
No, I wasn't going to. But basically, there's another map which I compare this to, which involves the compact cohomology and such, where instead of going to yf tensor xf, as psi f usually does, it goes to xf tensor yf. And then you compare the two maps somehow, and it falls out from that. It's a right. So if there were Selmer groups in the title still, then I would talk about that. But OK. OK. So Iwasawa theory. So let's let k over f be some big extension. I think I'll say it's a p-adic Lie extension. I'm only going to really need it abelian, but anyway, with Galois group G, for instance, the cyclotomic ZP extension. And for just simplicity in writing things, let's suppose that Sk, which is the primes over S in K, is finite. So I want to give you a use of these maps in terms of Iwasawa theory. OK, so now if I take inverse limits, so I take inverse limits up the tower for intermediate number fields, I get a map which I'll call psi k, which maps, and I'll have to define these things, uk to some Iwasawa cohomology, and then tensor xk. OK, so it looks the same. What are these things? So here, uk is the inverse limit under norm maps over number fields in K containing f of the UE. OK? H2 is defined similarly. H2 is the inverse limit under co-restriction over number fields contained in K of the H2 continuous cohomology with coefficients in ZP1, or for any module. OK, so that's those two groups. And xk is actually, I won't write it. I mean, xk is defined exactly as before. It's the Galois group of the maximal abelian it's the Galois group of the maximal abelian pro-p quotient of GKS, or the Galois group of the maximal unramified outside S pro-p extension, abelian extension of K. Same Galois group, but for K. OK, so now three, let me just write it here at the bottom of this board I used. So let's suppose I have an L
sorry, what does H2 sub S mean? Again?
It's the inverse.
Oh, that's the definition.
Yeah, that's the definition.
I guess it should be E, G-E-S.
E, yes. Typo. There. Okay, so, right, so now I'm going to take an L, which will play the role of my E. So let's suppose I have an L over K, which is Galois over F, unramified outside S. Right? Then I can define, as before, a map psi L over K and psi 1 L over K, which I'll do that in a second. But let's assume, for the result I'm going to state, that the Galois group of L over K is isomorphic as a Pro-P group, not necessarily Galois module, to ZP. Okay? It's procyclic. Then what's interesting is that these cup products, what do they do? I mean, this reciprocity map, sorry. What does it do? It tells you about the Iwasawa module YL, okay, so defined similarly, for the Kummer extension that I've defined here of K. Or it doesn't have to be Kummer because, in fact, note, from what I've said, K could be F. Okay. So here's the thing. Okay, how do I define UL over K now? I define UL over K, since L over K is a ZP extension. I can define it as the inverse limits, so the norm compatible sequences, which are norms for every finite extension in L. Okay, so the norm compatible sequences in K that are norms from every layer in L. Then I define my psi LK1. It maps to the same group again. It maps to YK tensor G. Here I have to, because I'm taking an inverse limit, I have to take the P completion of the tensor product. So that's what I do there. I mean, if mu were well, no, actually, I don't have to do that because G is ZP. So ignore that. Later. Okay. Now I have what I call a norm map from UL to UK. UL is just defined as UK. It's the inverse limit of norm compatible sequences. Well, if I have a norm compatible sequence of elements of units up to L, then I can just restrict it to the elements which lie in K, right? So I have a map which is just the restriction of sequences. I have a decomposition group at each V and S, K, and then I have this map sigma. Sigma is the sum of the injections of the decomposition groups into G. Okay. Now, YL maps to YK by restriction, right? So I should say what YK is, and YL again. Those are the Galois groups of the maximal unramified abelian pro-P extensions of K or L, in which all primes in S split completely. Okay? And those are no longer finite necessarily. Okay. So now the restriction map factors through the co-invariance by G because G acts trivially on YK. Another way of saying this YL co-invariance G is it's YL modulo the augmentation ideal in the why I'm writing. Okay, well anyway, in the Iwasawa algebra of G. Okay, right. So IG is the augmentation ideal, and just to save space on these exact sequences, I let twisting my module by G, I just put a bracket 1. So lambda G here, this is a lambda G equivariant homomorphism, this psi K. Lambda G, well, actually, yeah, lambda G is just ZP double brackets G, which I could have just used. Anyway, so this first sequence is doesn't involve the reciprocity map at all, but I just thought I'd show it to you for analogy. You see, the restriction map from YLG to YK fits in a 6-term exact sequence. Okay, it fits in a 6-term exact sequence involving the invariance and the co-invariance and so forth. You can do the same thing using this reciprocity map, rather more complicated, but for the second graded quotient. Okay, so that's what the cup product tells you about. The co-kernel of this map, this reciprocity map on ULK, is there's a map from the second graded quotient to it. The co-kernel and kernel are determined by the co-kernel and kernel of this map RLK, and then here you get the kernel, mod the universal norms, and so forth. So notice that this will be an isomorphism, for instance, if sk has just one prime. Because if sk has just one prime, this kernel and co-kernel are 0, so this map is an isomorphism. So this co-kernel and kernel are 0, so this map is an isomorphism. So I'll leave that up there for you to view. So that's another use of these. If you want to do the higher graded quotients, then one can actually define higher reciprocity maps, which no longer correspond to cup products, and get similar sequences for the higher graded quotients. Those sort of reciprocity maps wouldn't appear in local class field theory because you have a non-degenerate pairing cup product.
So those higher graded quotients have to do with Massey product?
Yes, right. That's where they're coming from. OK, so in my last 15 minutes, I want to talk about a conjecture. So for that, I'll need some definitions. So what is the interpretation of these reciprocity maps? Analytic. So this is, I just need to define a two-variable p-adic L function. So let's suppose that M is the inverse limit of the first cohomology groups of the modular. I'm going to take p to the n for simplicity, and what I'm doing, you could throw in an auxiliary n, big N, auxiliary prime to p. OK, so I take an inverse limit of these cohomology groups in a natural map. This has an action of a cuspidal Hecke algebra, which is an inverse limit. This Hecke algebra is an inverse limit of Hecke algebras of weight 2 and level p to the n over all n. I'm only going to need the ordinary part of this that one often considers. Let's let n, well, if I take the inverse limit instead over the open modular curves, this has an action for this particular group here has an action for a bigger Hecke algebra. So modular Hecke algebra, which surjects onto my smaller cuspidal Hecke algebra. Again, it's defined as an inverse limit. And so what I'll do to get a module for this smaller thing is I'll tensor over the bigger Hecke algebra with the smaller Hecke algebra. And so then I have a module, which I'll call n for h, and this one sits inside here, naturally. OK. So, right. OK, so now let's let n ord be the ordinary part of n. So this means that it's the maximal summand on which up acts invertibly. So up is the pth Hecke operator, right? So it's an inverse limit of pth Hecke operators in the finite sort of level Hecke algebras. So the two-variable p-adic L function, so I'll attribute this in a similar form to Maser and Kitagawa. So the two-variable p-adic L function, L, where does it lie? OK, it lies in the ordinary part of n tensored with some Iwasawa algebra. And now I really need a completed tensor product. Right, where lambda tilde is just going to be ZP cross, ZP double brackets ZP cross, is defined as, one way to define it is as an inverse limit. So this is really an element interpolating the two-variable p-adic L function, right? Yeah. Okay. So I take an inverse limit. To make things simpler, I'm going to take it over prime to p elements. Now that my UP is acting invertibly, I can apply UP minus n to a certain class of a path in the upper half plane, and I'll have, and then tensor by a group element at the finite level. Okay, so where do these elements lie? This is in z mod p to the nz cross. So I'm taking an inverse limit over the finite group rings in doing this, which gives me in the end something in here. And this, you might say, it doesn't lie in cohomology, it lies in homology. This is the class of the path from, right, in the upper, it's this way. So here's infinity. Here's j over p to the n. There's 0, right? So this is the class of that path in homology. But homology and cohomology are isomorphic, and, well, not canonically, but anyway, I make that identification. Okay, so I'm going to be a little iffy with how I'm saying this, but it's, all choices are made carefully. Okay, so, right. So also, but I'm not interested in the whole ordinary part. What I'm going to be interested in is a part of, so in H, there's an ideal called the Eisenstein ideal. Okay, and so the Eisenstein ideal, I, generated by, well, it's generated by UP minus 1 and all the other Hecke operators, TL minus 1 minus L times the diamond operator on L for all L not dividing P. Notice these are the coefficients of a lambda-adic Eisenstein series. So they're the coefficients of Eisenstein series. So basically, if I take, so let's let m bar, not n, I need m, to be m mod im. Okay, so what does this tell you about? It tells you about the modular symbols or the modular forms which are congruent to Eisenstein series modulo some prime above p. Okay, so mod p, they look like Eisenstein series. That's what it's telling you about. In fact, if I take L and I take my Hecke algebra and I localize it at the unique maximal ideal containing I, okay, so and then I sort of tensor my n here, so I'm lying in n localized at that maximal, not quite maximal actually. I want to take all eigenspaces at once, but anyway, if I look at it in the part coming from the Eisenstein ideal, then in fact this L doesn't just lie in n, it lies in the smaller thing m. Okay, so actually L reduces to an element L bar in M bar tensor with, actually now this is not needed. Okay, so now I'm ready to state the conjecture. Essentially, close. So a conjecture. So let's let K now be Q mu P infinity. Okay, so F is Q mu P. inside K, so I'm fixing, I mean, everything here depends, well, it doesn't depend on then, but anyway, depends upon choice of complex embedding of Q bar, which allows me to fix a generator of the Tate module. So say zeta is a generator, I'll write it, of ZP1, which allows me to identify ZP1 with ZP. Depending on, or the Tate module with ZP, really. OK. Right, so I need two maps. So the first map is, well, GQ acts on M, or acts on M bar. And the proof of the main conjecture by Wiles or gives, well, basically produces a map from the minus part of the Galois group, right, the Iwasawa module YK, the Galois group of the unramified extension, to homomorphisms from M bar plus to M bar minus. And this has a canonical generator up to my choice, again, of complex embedding. So I can take this to be M bar minus. So I define a map phi in this way. OK, so this is main conjecture, the standard main conjecture of Iwasawa theorem, the first one. It's been proven. OK, in this case, Maser. Okay. So, the second map is something that allows you to construct Kubota-Leopold p-adic L functions. So the second map is, you think of this lambda tilde. So lambda tilde is really canonically isomorphic via the cyclotomic character to ZP gal K over Q, because this is ZP cross. So you think of it that way, and you define a map phi prime from xk minus, so the minus part of this Galois group, to lambda tilde minus. So again, I'm taking a minus part. There's an element of order 2 in here, and I take the minus part. Given by, explicitly, again, you can take this to be, you take an inverse limit over n, sum I equals 1 to p then minus 1, ip equals 1. And then you take your Kummer character. Now this is a Kummer character to ZP1. Apply it to sigma, and multiply it by the group element I. So here, chi of 1 minus zeta p to the n to the I maps xk minus to ZP1. And I think of ZP1 as ZP, so I get coefficients in ZP here. OK, so I take a log, if you like, with respect to zeta. OK, now two more definitions, which are simple ones. 1 minus zeta is the norm-compatible sequence 1 minus zeta p to the n that I've coming from my chosen generator. Three more definitions. Yeah. Psi k, I just need to modify my map psi k very slightly. Just project to the minus parts on both components here. Both. OK, minus and minus. Again, I already defined L bar. But instead of this L bar, let me just modify this here, I will take minus part here and here. OK, L bar will be in the minus parts of both components. OK, so the conjecture. there is a unit, and this unit does not depend upon any choices that I've made. Okay, there is a unit in this Iwasawa algebra such that setting C to be the tensor product, so I multiply my map phi by this unit, and I tensor that with phi prime. So this gives me a map from where to where. I should review that. It gives me a map from yk minus tensor xk minus to m bar tensor minus tensor lambda tilde minus. And then the conjecture is that if I take psi k, I apply it to my inverse limit of 1 minus roots of unity, and psi k circ, that gives me an element here. I then apply this map C to it, ck. And what do I get? The two-variable p-adic L function reduced modulo the Eisenstein ideal. OK, so that's the conjecture. So what is this telling you? Explicitly, it's telling you that values of the cup product pairing I was looking at earlier are related to specific p-adic L values for a given level and character, weight level character. Specific p-adic L values of, well, not really, of cusp forms that are congruent to Eisenstein series mod p, or more all at once in some way. So that's the conjecture. What evidence do I have for this? I don't really have time to mention, but I'll mention it out loud. Under some condition on divisibility of Bernoulli numbers, there exists an extension L, okay, so that if I tensor yk by its Galois group, this is not necessarily cyclic, so I have to take co-invariance for gal k over q. Then this is isomorphic to, so this is under some assumption on Bernoulli numbers. This is isomorphic to the Eisenstein ideal mod at square, and the element psi L over k 1 minus zeta in here maps to up minus 1, which is somehow telling you about an L value at a trivial character. This is not exactly direct evidence. This is an earlier result than before I made this conjecture, so I'm not doing it chronologically. And what this tells you about, actually, if you go back to my exact sequences, it tells you about the second graded piece in the Iwasawa module of L, that in fact it's I mod I squared plus the subgroup generated by up minus 1. OK. And this is actually one last thing. This is how I proved that the map psi f p through root of p over f is surjective for p less than 1,000. I showed that up minus 1 generates this Eisenstein ideal. OK, thanks.
Are there any quick questions?
An obvious question. Where does the ambiguity about the choice of sigma or of zeta disappears?
OK, so this map depends upon everything I chose. Well, most things depend upon the choice of zeta, which comes from the choice of complex embedding. The map, in fact, depends upon the choice of zeta. And the 1 minus zeta also depends upon the choice of zeta. But when you put all of the choices together, it doesn't depend upon the choice of zeta anymore. That's somehow the point. I mean,
And you can see it.
yeah. I mean, it's a different map, but it's also a different 1 minus zeta. And so the ambiguity disappears there. I mean, there is some ambiguity in U. It's not canonical because, of course, this is torsion for lambda. But in that sense, it's independent. I mean, it's complicated to see, but everything basically depends upon this choice. And even you even have to show that sort of locally you can choose a decomposition group in such a way that the fixed part of m bar, the fixed part of m by the inertia group is equal to the plus part of m, and various many choices that come in, but in the end, yeah, it all disappears. Conjecture.